Good evening, everybody. So, welcome to this session on quantum computing using Qniverse. So, today we have Dr. Manprit Singh with us, who will be taking this session. So, Dr. Manprit Singh is a physicist whose research explores quantum phase transition, cold atoms, non-equilibrium dynamics, superconductivity, and ferromagnetism with relevance to the quantum computing and related areas. He earned his bachelor's degree in physics from the Institute of Excellence in Higher Education, Bhopal, and went to complete his integrated MSc PhD in physics at the Indian Institute of Astrophysics, Bangalore. He has been awarded prestigious fellowship including National Postdoctoral Fellowship and Marie Curie Fellowship to work at IIT Guwahati and University Paris, respectively. Currently, he is working as an adjunct engineer in C-DAC Pune. So, starting from beginning, we have gone through the basics of the quantum computing. Now we are moving into the algorithms. Today we will be dealing with variational quantum eigensolvers, and Dr. Manpreet Singh will be taking us through the session. So, Dr. Manpreet, over to you. You can start sharing your screen and start the session.
Okay, so thank you for the kind introduction. And once again, welcome everyone. So let me just start sharing my screen. So is it visible?
Yeah, good to go.
Okay. Okay, so I hope by now all of you have picked up some of the basics of quantum computing and are now somewhat familiar with the Qniverse platform. So continuing from that and moving forward, today we will be discussing the variational quantum eigensolver (VQE), and also we'll see how can we implement it on the C-DAC Qniverse platform with a hands-on session. So before coming to what is VQE, we should first look into the need of such methods, like why is VQE or some alternative method needed for the calculations what we want to do. So for physics as well as chemistry related problems, the entire problem boils down to basically calculation of the ground state energy. So which just means that we are trying to find a stable configuration of a system. So it can be like two atoms interacting with each other, or it can be some kind of lattice model in which there are many spins arranged on a lattice, and we are trying to find out the ground state of that system, and so on. So when we are dealing with these systems classically, the most commonly and most ubiquitous method is the exact diagonalization. But that works only for small systems, and as the system size increases, for example, if we go on adding some lattice sites, or we go on increasing the system by adding more and more atoms, the size of the Hilbert space grows exponentially, and because of that, the computational efforts needed to solve that problem also increases exponentially. So by now, I think all of you must be knowing that quantum computing can help us here in a very big way. Because first of all, these quantum systems offer a natural scaling. As you know that on addition of one qubit, you can just double the Hilbert space, or double the computing space immediately. But that is not true for the classical system. So you need you need to increase the memory and other computing resources drastically. So, and also for the current state of the quantum computing systems, which are still in the NISQ era, VQ is a very suited algorithm. Why? Because see, VQE makes use of quantum computers as well as a classical hardware. So it can basically make use of the power of both the computing devices, and that's why we hope that it will give us a big advantage in this scenario. So that's why you can like kind of say that okay, VQ is one of the most promising algorithms for the NISQ era, which enables some practical quantum advantage in areas of physics, chemistry, materials, and optimization. Okay, now coming to the VQ itself. So what is VQE? So like to quote from the famous quantum mechanics book by David G. Griffiths. So you start with some any normalized function psi. It can be anything. Okay. And now you want to calculate the ground state for some particular Hamiltonian. Okay. So you for which you don't know the exact ground state, say psi naught. Okay. So you start with any normalized wave function psi and then calculate the expectation value. So the variational principle says that you will always end up with some energy which is at the best equal to the ground state energy. Otherwise, it is just above that. So what one? So what? So the trick is to design this wave function or the trial wave function, which we call, in such a way that it depends on some parameters, say 10 parameters, 15 parameters, in such a way that you have the ability to control these parameters. And what you can do is you can fine tune these parameters in order to find out the minimum energy value you can obtain. So once you go on tuning these parameters, like in a loop kind of thing, you will end up with many such values, and the energy value, which is the minimum one, is the closest or equal to the ground state energy of the system. Okay. So, okay, next. Okay. So now we want to just see, like, in mathematical language or computing language, what does it mean? So we start with some arbitrary psi, and then we find out the expectation value, which gives us a value which is always greater than or equal to the true ground state energy, which is E naught. So when we want to compute such a thing, what we can do is we can introduce a parameter theta, for example, and make this make this trial wave function dependent on this parameter theta. And then we go on adjusting this theta so that we achieve a minimum of the energy, which we can then say that it is a good approximation to the true ground state. Now, what we want to do is we want to implement this entire thing on the quantum computer along with the classical counterpart. Okay. So before going into the implementation part, first what we should look into is the physical system which we are going to deal with. So ideally, like physical system can be comprised of spring and mass system, or spin or lattice problem, ions and electrons in a crystal, or atoms in a molecule, which is what we will be looking at today. So after we have chosen a physical system, or we have fixed a physical system which we want to look into, the next logical step is to describe this physical system in a mathematical way or in a mathematical model. So to do that, we describe it using a Hamiltonian. What is Hamiltonian? Hamiltonian is nothing but a model which gives the sum total of the energy contributions in that physical system. For example, for a simple system, it can be just a sum of kinetic energy plus potential energy. And also, we need to choose a basis to represent this system. And apart from that, we need to fix the parameters for which we want to determine the energy. And after we have done that, we can go in the next step where we find the actual energy of the system using some method like solving the time independent Schrodinger equation. So today we will be looking at the example of a hydrogen molecule and water molecule. So in this system, in both of these systems, the main contribution of the potential energy comes from electron-electron interaction, nucleus-nucleus, and electron-nucleus interactions. The kinetic energy basically comes from the motion of the electrons around the nucleus. And to define the basis for the electrons moving around these atoms, we can express it in the spin orbital form or occupation basis, which is to say that we can always say that if some spin orbital is occupied, we can assign some value, say 1. If it is not occupied, we can say 0. And the parameters for the system, for these simple systems, are basically the interatomic distance, or the distance, the separation between the two nucleus. And next step will be to determine the energy of these configurations using VQE. So now comes the formulation of the problem. So we know that we have to define a Hamiltonian. So what does this Hamiltonian comprise of? So this Hamiltonian will comprise of the kinetic energy, which is basically because of the electrons, and the potential energy, which comprises of the electron-electron interaction, electron-proton, and proton-proton or nucleus-nucleus interaction. So the first term here, it basically gives the kinetic energy contribution. Here we are working with the Born-Oppenheimer approximation, and under this approximation, we assume that the position of the nuclei are fixed. So there is no kinetic energy contribution as such from that part, and the only kinetic energy contribution comes from the motion of electrons around the nucleus. And then for the potential energy, we have the second term, which gives us the interaction between the two nucleus, and then this third term gives the interaction between the nucleus and electrons, and the last term gives the electron-electron interaction. So here Za and Zb are basically the proton numbers, or you can say charge in the nuclei. So if both the atoms are identical, then Za equal to Zb, and in a simple case like hydrogen, there is just one proton, so this just so Za Zb term just reduces to one. Okay. So now comes the definition, like how do we define the basis? So a natural way to define the basis is using slated determinants. So for any general system, uh, one can define a wave function psi, which is dependent on x1, x2, x3. So these are basically the electron coordinates. So each x1, x2, or xn contains the spatial as well as spin information of the electron. And on the right hand side, what you see is first term is just normalization factor, and within the determinant, so you see the arrangement of the orbitals, basically like which orbitals are occupied, how are they correlated, and so on. Like so, all the information about all the electrons in all the orbitals is encoded in this later determinant. So there are some interesting properties which are already like inherited in this kind of structure. For example, we know that for fermionic systems, under the uh, exchange of the particles, antisymmetry should hold, and also we know that there should be Pauli's exclusion principle valid for this case, because electrons as electrons are fermions, you cannot put them in one orbital together. So that is what we see here. So so to understand it, you just, I mean, we can just concentrate on say two columns. So when we say that we are changing the position, interchanging the position of two electrons, what that means is we are basically transferring or interchanging the two columns. So what that translates to, it will change the sign of the whole determinant. And when you try to evaluate it, you will see that it is basically the same thing what you obtain when you change the position of the electrons and do this calculation ordinary. Like for example, as you see in this point number one, for psi x1, x2, x3, and so on, under the particle exchange, it just becomes minus of psi x2, x1, and so on. Also, Pauli's exclusion principle holds. That means if you try to put any two electrons in one orbital, so so for the electrons which you are fixing the orbitals or trying to make them identical, so we will end up with two identical columns, which will just end up making this determinant as zero, which is again giving the validity of holding up of Pauli's exclusion principle. So sometimes this kind of determinant or this notation is written as chi1, chi2, chi3 for brevity. So this approximation is good but not accurate, because what we are doing is we are not taking into account the relative position of electrons, but just kind of a mean field interaction. But in this case, it is good enough. So to understand better, we can just look at the example of hydrogen molecule, which will also be a part of the demo in Qniverse. So for hydrogen or atom, each atom has one s orbital, and each orbital has mm, uh, possibility of accommodating two electrons. So for two atoms in a hydrogen molecule, we have a total of 2 spin orbitals along with 2 spin contribution. That gives us in 4 spin, that results in 4 spin orbitals. So if we want to express the wave function in terms of Slater determinant, what we have to do is we have to choose 2 orbitals out of 4 at a time and then make the combination like the one shown on the screen, and then take a superposition of all these sides to express the entire wave function. Okay. So now we have the information on the general Hamiltonian and the expression of the state, but that is not good enough because we still want to translate it to some language which is more friendly for a quantum computer or coding wise. Okay. So to do that, it is better to use or to formulate it into some convenient form, which is also known as a second quantized form. So in this second quantized form, what we do is the operators. We talk in the terms of operators, which are like AP dagger and AP, so which are also known as creation or annihilation operators. The function of these operators is to basically create one particle and destroy one particle. So, for example, if I say A dagger P, what it does is it creates one electron in the p orbital, and if I say AP, it is a destruction operator, so it will destroy one particle in the pth orbital. This is a natural language and very intuitive. So if you want to express some wave function psi in this language, then we can just start from the vacuum state and then apply these operators and create any arbitrary state. So what you see is you can always define some state like n1, n2, n3, n4, and so on, and apply these operators to define a particular state. So also, the structure of these operators is such that they follow the anti-commutation relations, which is what uh, should be the case for the fermionic species. Okay. So now again, looking into the hydrogen atom example. So what one can do is we can, as we saw that we can have 4 orbitals. So this can be the arrangement. Okay. And if we want to represent them in occupation number basis, we can always express them in cat notation. So, for example, you can see that the cat notation shown here are like 1100, 1010, 0110, and each of them has 4 indices. Like first, for example, in the leftmost one, the first and second are 1, and third and fourth are 0. So these are orbital indices. So you can see that the first index corresponds to psi 1, second one to psi 2, third one to psi 3, and fourth one to psi 4. So if a particular orbital is occupied, you can assign the number 1, and if it is not occupied, you can assign 0. So now it becomes more friendlier and intuitive to code a quantum computer or a classical computer. And now to look into the mapping of the Hamiltonian into this formalism. So when we try to, okay, so in the second quantization, the Hamiltonian looks like what it is shown on your screen in the yellow box. Here, HPQ and HPQRS are basically 1 and 2 electron integrals, which in simple terms means that they contain the contributions from a single electron and 2 electron. So single electron means like it can be nucleus electron interaction or the kinetic energy of a single electron, and 2 electron integral basically handles electron-electron interactions and so on. And after doing that, all we want to now do is map it into qubits. So that we will be using the poly operators, which are in the standard format shown here. And also these are like convenient to use for this quantum computing, and all the measurements are done in this basis. Okay, and to map these operators into this qubit form, we basically use Jordan-Wigner mapping, which is shown here. And then after you apply this mapping, the Hamiltonian reduces to these poly operators, which are again for hydrogen molecule. This Hamiltonian is shown here. This is all now coded into the qubit format. So here the coefficients, what you see here, like B1, B2, B3 till B12, they are all dependent on the internuclear distance. So that is already taken care of in our Hamiltonian. Now coming to the implementation part. So as stated earlier, before using VQE, we need to parameterize our quantum circuit and choose a suitable trial wave function, which we also refer to as ansatz. Okay. So some of the popular choices for defining or choosing ansatz are efficient SU2, hardware efficient ansatz, or this unitary coupled cluster with singles and double excitation. So this is what we will be using in the demo session or hands-on session. So about UCCST, so it basically comes from the coupled cluster theory, which is a very powerful chemistry tool and quantum chemistry tool used for the calculations beyond mean field. It takes into account the strong electron-electron correlations, and it is systematically improvable by including higher order correlation corrections, which are also sometimes referred to as excitations. And it is sufficient to use it with singles and doubles in the following session, what we'll be seeing later in this webinar. So for the reference state, we start from a Hartree-Fock state psi naught. And for the excitation operators, we just consider singles and doubles. So what do they mean? That singles include the promotion of, like, promote one electron to some other orbital, and doubles means to promote two electrons to two other orbitals. Okay. So now coming to the general VQE pipeline. So what you see here is a very like bird's eye overview kind of description of the entire process. So we start with a initial state which has some and dependent on some parameters theta naught, and then this theta naught, depending on this theta naught, I mean, you supply to the quantum device, then the state is prepared for in the quantum device, and then further some measurements are made, and after those measurements are made, the information is passed on to the classical device, which measures or calculates the expectation value for this mm, action of after this action of measurement. And if we feel that this is not optimized, we can run the loop again and supply back this uh, uh, next wave function by tuning the parameters again. And again, this process repeats. This measurement happens, and again we calculate the energy. This process is continued until we feel that this the value of energy has converged. So once it is stable and no longer changes, we can say that the process is complete and the energy value what we have obtained is the close to ground state or the exact ground state. So, like in computing, in the terms of, if you're talking in the terms of gates and qubits, so what we are going to determine is E as a function of the parameters theta, and then this Hamiltonian is basically acted upon by this. This psi naught state is acted upon by this u theta, which are just the gates, and this phi naught are coded in the qubit form. Okay. So once that is done and this thetas are tuned, we can obtain the optimized energy values. And if you want to look at a detailed, in-depth pipeline, you can always refer to the documentation given on the Qniverse website, so which gives you a more detailed view, like how the different processes are happening within this calculation. So the parts you will see in the blue are basically the parts which are implemented on the traditional classical computing hardware, and the parts which you see in yellow are on the quantum hardware. So like, and so these are some more things which I think we should discuss about. So first step is to define the system, which you already seen, then basis selection, Hamiltonian representation. The second major step is the encoding of operators into the quantum computer compatible format. Third step is the measurement strategy and grouping. So, okay. So for here, by grouping, what you mean is we had defined this, we obtained this Hamiltonian in this form where we had this x, y, z terms and so on. So what we want to do is we want to make a measurement on this. So this is what it refers to here. And then we want to repeat this circuit many times. So what you want to do is you want to make sure that the entire process is efficiently coded so that we can obtain the results in minimum number of runs or with minimum number of executions. Okay. And also one of the next step is ansatz and state preparation. So we prepare the initial trial wave function and then decide on ansatz whether we want to keep UCCST hardware efficient or something else. And then we enter the VQE loop where the all this process is happening, this measurement process, and then combining the measurement results to obtain the energy which is shown here in the right hand side. Take the weighted sum of all these and then find the energy values. And then finally it goes to the classical optimizer which checks uh, whether we should keep this energy or we should optimize it more and run the loop again or not. Okay. So now coming to the hydrogen molecule problem. So what is the nature of the problem? So what we want to mm, find is like given two hydrogen atoms, uh, under what conditions can they form a molecule, or like if a molecule formation is possible at all, and if it is possible, what is the distance or the equilibrium separation which will be there in this hydrogen molecule. Okay. So on the right hand side, you see a intuitive picture which gives you the relation between the potential energy and the equilibrium bond length between these two hydrogen atoms. So when they are sufficiently far apart, they are interacting by van der Waals kind of attractive forces. But when they are very close enough, they start repelling because of electron-electron and nucleus-nucleus repulsion. So, but between these two states, there will be one configuration at which this state is stable. So that is also known as, so that is what we call as a equilibrium bond length. So using VQ, what we want to do is we want to calculate the energy at each of these uh, separations, which are shown by a red line, and then calculate the energy at each step to see like which one of these corresponds to the absolute minimum. The energy or the separation at which the minimum energy is obtained, that will be the equilibrium bond length. So now just we can just go and have a now just we can move on to the Qniverse hands-on and see how it is implemented there. So if you already have an account, you can just log into this Qniverse portal. Or if you don't have, then you can just register and obtain an account. So after logging in by entering your username and password, you will end up with this screen. Then in the top left, from the top left corner, you can access the drop down list. So, and after you do that, uh, you will be seeing this drop down list. Here you can select the algorithm part, and after selecting this algorithms, you can scroll down and choose Variational Quantum Eigensolver as the algorithm. Within that algorithm, you will see there is a list of molecules already given there. So like beryllium hydride, then water, hydrogen, lithium hydride, and so on. So select the hydrogen molecule from this drop-down list. And after you've done that, you can just press the load circuit button in this box. So once you do that, you will be prompted with this kind of box which says select wiki preference. Here this first and second row are basically used to define the geometry of this hydrogen molecule, or like where do you want your hydrogen molecules to be placed in the Cartesian coordinate systems. So the units are basically in angstrom. So for uh, like convenience, what we can do is we can place one of the hydrogen molecules at the one of the hydrogen atoms at the origin, which is defined as 000, and the second hydrogen atom we can place at any arbitrary and reasonable distance, and for example zero point 0.7 units, which is shown here. Then after you have defined this coordinates, you can just load it. After pressing the load, just yeah. So you will see this following code which gets loaded into your uh, interface, Qniverse interface. So there are many lines which you see here. Let us try to understand what do they refer to. So first line, uh, which is like input molecular energy. So this is for setting up the problem, and it also contains references to exact solution and VQE solution. It basically defines like, okay, so what we want to do is we want to define the problem of hydrogen molecule energy estimation at a particular internuclear separation, and also you want to check whether VQE solution, how good is our VQE solution. So for that, we will match it with the exact solution, and the definition of exact solution is defined within this. So basically, exact solution just does the exact diagonalization using classical methods and gives you the energy. And then second line basically imports the molecule info. So it is a library of all the molecules, and along with that, what you can customize is the coordinates, what we already did, then charge and multiplicity. And for this demo, because it is a hydrogen molecule and there is no, I mean, no electrons have been added or removed from the system, so charge is zero. And next step or the next line is PyCF driver. So this is a Python-based simulations of chemistry framework. It is used to analyze the molecular structure and then just passes on the defined molecule the PySCF driver, which computes the molecular integrals and returns the essential electronic structure properties. In the next line, you will see the mention of freeze core transformer. So for a hydrogen-like atom, basically it is just one electron, and there are no other electrons to take care of. But if it is a much larger atom, say for example oxygen or even larger atom, so what you want to do is we want to make our problem simple, and to make that we make an approximation that all the inner electrons are basically static and they are frozen. So that is what this freeze core transformer does. Okay, and then we define the molecule which contains the molecule info, and it is connected to this import molecule info line here. Then these are other parameters which you need to take care of, and these are the definitions. So driver computes the integrals and properties of different molecule. Then properties is equal to driver dot run runs a PyCF calculation. Then this freeze code transformer implements the transformation of the molecular problem by freezing these electrons or core orbitals. Then we have VQE molecular energy, which initializes the molecular energy calculation object for VQE. And this final line just calculates the VQ result and the final result, and then compares, and then we can compare the two. Okay. So there are some other important things or parameters which we need to take care of. So the distance, as I already mentioned, is in angstroms. Then the basis selection is done by default in STO3G, which is Slater type orbital, three Gaussian function basis. So you can, so it is like each electron orbital is approximated by three Gaussian functions, and the parameters or the coefficient for these Gaussian functions are chosen automatically. But one can go for higher approximations like six Gaussian and so on. Then there is a parity mapper which converts the molecular Hamiltonian into a qubit representation, and then there is selection of ansatz. By default, it is UCCST in our simulation, but you can always experiment with some other answers. And there is optimizer and estimator. So for this simulation, we use SLSQP, sequential least squares programming optimizer, which is a gradient based methods. But one can also experiment with like Cobila, SPSA, or other optimizing algorithms. Okay. So once we have loaded this code in this Qniverse interface, you can click on the run button, which is on the top right corner. And after you do that, you will see a job ID, which indicates the ID of the job which you have submitted right now. And then there will be a wheel kind of a structure, rotating wheel kind of a structure, which indicates that your job is being executed. So after you click on the job ID, it will open this kind of a screen, which will basically give you the job ID, circuit ID, and then also it will show you the time at which your job was created and what is the current status of your job. So whether it is in queue or it is running or it is completed. So depending on the platform you have chosen to run on, whether it is this CPU or GPU or some other platform, the time can vary, but it can take around maybe 20 seconds or so, 20-21 seconds. And to check the status, you can always press a refresh, and after you see that your job is completed, the output will be dumped to this screen or box which is shown on the right side in the bottom section, the second part. So here you will see the number of iterations being carried out and how your energy value actually is converging or changing. And finally, when this job is complete, the final calculated energy will be shown at the bottom of this output. So you can repeat this entire process for different number of interatomic separations. So, and after you have done that, you can actually plot the energy on y-axis as a function of the internuclear or interatomic separation, which is on the x-axis. And once you do that, you will see that this minima in energy is obtained at 0.74 units, so which is what is actually the true interparticle or interatomic separation you obtained using the classical computations also. So you can repeat the entire process for water molecule to see how does the structure of water molecule come up in this, like, because we know, okay, so it is not a simple case. So because once you do this simulation for water molecule by defining the position of different hydrogen atoms and the oxygen atom, and then once you load this circuit and run it, it will take some time for the simulation, much more than this hydrogen atom calculation. And then once you are done with that, uh, you will get a lot of output lines, and at the end of this output you will finally get the energy, converged energy for this system. And once you do sufficient number of runs and sufficient number of permutation and combinations for this coordinate geometry, you can actually find out the position, equilibrium position of hydrogen as well as oxygen atoms. So yeah, so here are some of the references you can actually go to if you want to find more details for the variational algorithm and the introduction to hydrogen atom and molecule. You can refer to the book by DJ Griffiths on Introduction to Quantum Mechanics, and the Qniverse documentation you can refer on this link given here, which basically discusses the variational quantum eigensolver and uh, what are the uh, finer details which are included in this simulation. And for the quantum computing part and the circuit implementation part, you can refer to this archive paper and also to the notes on this variational quantum eigensolver by Stephanie R. Simeonidou. And then, of course, you can uh, find out more details on the IBM in the IBM Cascade documentation and the tutorials uploaded by IBM on the YouTube channel. So with that, I would just to thank you. And if there are any questions, I think you can ask now.
Yeah, if anybody has any questions, you can type it in the chat box. So meanwhile, the first question I will ask this one. They are asking like, by considering hydrogen problem as many body problem, what computation we need for this solution? Why everyone considers this hydrogen problem rather than choosing any other problem?
No, no, as I have shown, okay, so hydrogen atom is like one of the simplest cases what we can consider and to like understand the finer details. So you don't want to start with a very complicated problem immediately. So as I have shown that you can do the same kind of simulation for for water molecule or even benzene molecule and so on. And also, okay, so benzene and these kind of molecules are also, they may seem simple, but for the current state of quantum hardware what we have, which are still in NISQ regime, it is not possible to do lengthy calculations because these are limited by coherence times. If the execution times exceed, then you may end up getting more errors. So if you have a lot of errors, then I mean, you will need more error correction and so on things. But if it is error prone, if a calculation is error prone, then you will not get anything useful. So that is, I mean, that is the main reason why we want to consider simple molecules for now.
Uh, Next one question is, see, what are the other hybrid methods that can be used for VQE solving, other than VQE for solving the what is that, ground state energies?
So you can use this QAOA method also, and then so okay, so this VQ currently I've shown you as a it is implemented on gate-based machines, but you can also use some algorithms which are more suitable for D-wave kind of machine, which do this energy calculation by optimization. So for that, like you can use QAOA method, maybe that is more suitable.
Next one question is, can we use only quantum approach to solve these kinds of problems? Will these methods provide advantage compared to hybrid and classical methods?
Sorry, I did not understand that question. Can you please repeat? So,
So can we use only quantum approach to solve these kind of problems? Will these methods provide advantage compared to the hybrid and classical methods? Is there any quantum advantage? That is the question for solving these kinds of problems as of now.
as of now, I don't see. I mean, these are comparable. These are still like in testing stages, benchmarking stages. So, like practically for now, using state of the art HPC machines and so on, we can do calculations for much larger molecules. But I mean, yeah. So what I feel is like in future, it will not be just the quantum computers or quantum devices alone. So it will be like ecosystem of quantum as well as HPC architecture. Uh, so the load will be distributed. Some part will be on the quantum machine, some part will be on the classical machine, because so it okay. So you can understand like GPU and CPU combination. So not everything is optimized for GPU and not everything is optimized for GPU, CPU. So for example, if you consider matrix multiplication, matrix vector multiplication, so these kind of things are done very quickly on the GPU machine, but CPUs are not suitable for that. But again, so GPUs are not like you cannot use GPUs in place of CPUs. They cannot replace them. So that is what something I would say.
Okay. Another question is, what differentiates VQE with other variational algorithms like QAOA? What kind of problems are suited for VQE and QAOA respectively, and why?
Okay, so for Q, okay, so I mean they are basically kind of similar algorithms. There are not many differences. So it is just like I feel like this wiki may be more suitable for gate-based kind of machines, and this QA is more suitable for optimization kind of machines, like your D-Wave machine and so on. So, and for like the problems which you can deal are like what we've already seen. So there are some of the examples which I've already discussed. Apart from that, you can use uh, this optimization kind of routines for solving some problems like traveling salesman problem, where one tries to minimize the traveling path or the total travel time um, for a person to move through a chain of cities. Or you can also look into some other optimization problems which are uh, science motivated. And yeah, so basically that is it.
Next one question is what advantage VQE has over annealing methods?
uh, Advantages, mm, I mean, these are two different things. Yeah, so that I immediately I cannot answer. I have to uh, look into it a bit. Like
Okay.
one-to-one correspondence, I have to think about it.
Next one question is like, is there any VQ will be helpful in QML? Is there any way it will be helpful in quantum machine learning?
Mm, no, I cannot comment on that. I don't work on this. I've not looked into this kind of thing. Like how can we use VQ and QML? Mm, no, sorry, I cannot comment on that. So,
Okay. And one question I would like to answer, like somebody was asking, like, can we have all the videos? Can you get all the videos of all the sessions? So we would like to inform that all the sessions, whichever is happened so far, and whatever is coming in the upcoming sessions, also will be available in our YouTube channel. So if you go to our YouTube channel, you will all the recorded sessions will be available. Any other questions? I think we have taken almost every questions whatever has come in the chat box. And if you have missed out any other questions, you can send us a email to the mail IDs whatever we have provided, or directly you can send it to Manpreet also. So if there is any more no more questions, we will wind up the session. I would like to thank Dr. Manpreet for sparing his time and having a wonderful session in the evening. And we hope all of us will be back for the next session in the webinar series. So till then, bye from C-DAC Bangalore. Thank you. Thank you, Manpreet.
thank you.